Okay, so for today's session, I'll be going through the Fourier transform and basically how to get a frequency response. So first thing to remember is the following property of a system, that whenever you apply a complex sinusoid as an input to your signal system, your output is just the frequency response of your system at that frequency capital omega and the sinusoid at that frequency. Okay? And this is continuous time. You have an analogous representation for discrete time. Okay. Now, how do we get this? How do we know this? So let's say our input xt is e raised to power j capital omega t, right? What will be my output? Y of t. No, that's something that we need to prove. How we got to this point? Correct. So basic h of t convoluted with x of t, right? That's how your system works. Okay. Now expanding on this, we know how to take the convolution. So my it's x of t minus lambda and h of lambda d lambda. I can either go x of lambda and h of t minus lambda, either way. Okay. Now next thing is that I can pull out the t. So I have e raised to j omega t minus into infinity h of lambda e raised to power minus j omega lambda d lambda. What does this correspond to? Correct. The Fourier transform that you take, right? Because in Laplace you have e raised to power minus s of t. Okay. So you have e raised to power j omega t multiplied with the frequency response of your system function. Okay. So there is a reason for this representation. It's not out of the blue. Okay, and this is the reason. All right. Now, whenever we talk about the frequency response, we have its magnitude and phase. Okay. So whenever you are asked to plot the frequency response, plot both the magnitude and the phase. All right. And while just labeling your plots in exams, in homeworks, just be sure that you're labeling it correctly. So your x-axis or the horizontal axis is not n or t, it's omega. Okay, it's frequency response. And then you have your angle of h, again with respect to omega. Okay. Another thing is that your magnitude response is symmetric about vertical axis. All right. It's not that you only have your magnitude only for non-negative frequency values. Okay. It also extends to negative frequency. Physically, there's no notion of negative frequency, but this exists because our signals are real. Okay. All right. So next thing, let's just do a quick example. So all of us know what ideal delay is, right? And I'll do this in discrete domain. So when I'm in continuous domain, I'll take its Laplace transform. When I'm in discrete domain, I'll take the Z transform and then convert to the frequency. Okay. So in discrete domain, this is how I will represent my ideal delay. Any questions on that? No doubts? Okay. So what is y of n in terms of x of n? What is the output? No, I'm still in the discrete time domain. I've not gone to z domain yet. Just x of n minus 1. That's your output. That's what the system is doing. It's delaying your input by 1 unit. Okay? Now I will go to the z domain or the frequency domain. So what is my impulse response? You can say that easily. So my impulse response is the output when my input is an impulse. So what will be my output? Yeah. H of n is my impulse response. No, it's delta of n minus 1. Okay, because this is your input and h of n is your output at that point of time. Okay? So be very clear with the terms of impulse response, step response. Okay, we'll just revise this again. Alright, so I can take Fourier transform directly, or I can go from z domain to frequency domain. So let's take the z transform. What will be my z transform? Oh, sorry, z transform of this equation. Y of z is equals to z inverse x of z. So my h of z is equals to 1 over z. Sorry. Correct? And for going from z's transform domain to frequency domain, what do I do? Okay. So first of all, what is the ROC? This should be easy. Correct. Or z not equal to 0. Because z can be negative or positive. We are talking about a circle, right? Not a line or anything. Okay? So z not equal to 0. And when the ROC includes the unit circle, then I can make a substitution e raised to power j omega. Okay? When I go from S to frequency domain, then it's j omega. When I go from Z to frequency domain, it's e raised to power j omega. Okay? So now what is my frequency response? Easy, e raised to minus j omega. Correct? Okay, so quickly, let's get its magnitude. What is the magnitude? Sorry? Magnitude of e raised to minus j omega?
1.
1. And what is my angle? Minus omega. Right? As my omega changes, my angle will change. Correct? Okay. Any questions till now? Yeah.
So you said that we substitute e to the j omega for
That's right.
discrete, and what about continuous again?
S is equals to j omega, I believe. Yeah. All right. Okay. Now let's discuss about discrete filter analysis and how we can tell from the pole zero diagram itself whether it is a low pass, high pass or band pass. So are we clear on the types of filters? No. Okay. So let's first go to types of filters. So when I say low pass, for example, what do you think it is? What is it passing?
Low frequencies.
Correct. So it's passing low frequencies. Sorry. So if I have a magnitude response like this, let's say omega, and let's say it's mod of h omega, for example, what sort of a magnitude response would I have if it's passing low frequencies?
Starts high and high.
Correct. So something like this, correct? And this point, I mean a point over here, will be my cutoff frequency once it gets constant. Okay? So after my cutoff frequency, everything is attenuated. I'm not passing anything. Okay? And below my cutoff frequency, I'm passing my signal. So ideally, let's say ideally this should be like this, right? But we all know that we can't have such a sharp transition. It's not physically implementable. That's why we have a sort of a roll-off, a smooth roll-off, instead of such a sharp transition. So this is my ideal low pass. All right. So low pass is done. High pass is just the opposite of low pass. So my ideal high pass will look like this. This is my cutoff frequency omega c. Okay. Up till omega c, it's not passing any frequencies, any frequency content, and after that, it'll pass that frequency content. Okay. Now, realistically, again, this would have a roll-off. And we have it on both sides, again, because we're dealing with real signals. All right? Okay. Now, let's look at bandpass. So, bandpass can be thought of as a combination of low pass and high pass. It only passes a specific band of frequency. So, let's say if I only want to pass frequencies from 10 to 40 kilohertz, right? So my bandpass will look like this. Okay. My ideal bandpass will look like a rectangular pulse. Okay. All clear till now? Now, next comes band stop, which is absolute opposite of bandpass. All right. So your response will now look like this, and your ideal should be this. Okay. Absolute opposite. All right. That is done. So now all pass. Evident from the name, it just passes all the frequencies. So it has a flat response for all frequencies. Okay. And now if I come to notch filter. So notch filter, yeah, sorry. Notch filter you can think of as band stop, but it is only for a single frequency. With band stop, you're filtering out frequencies in a particular range, like 10 to 40 kilohertz. With notch, I'm only filtering out 10 kilohertz. Okay. So my notch filter will look like this. Okay. It filters out 10 kilohertz. Okay, so does not pass a particular frequency. Notches it out. Alright? All cool now? Okay, so from the pole zero diagram that we get, so if you have a discrete time equation given to you, from that you can go to the z domain, from that you can go to the pole zero diagram, and once you have the pole zero diagram, you can predict the characteristic of the filter. Okay? Now, how to do that is the next thing. Okay, so one thing to remember is poles represent passband and zeros represent stop band. So if for a particular frequency, if I have a pole at that location, my filter will pass that frequency. And if I have a zero at that location, it will stop that frequency. Okay? Now, let's quickly look at this. So I have my real z-axis, imaginary z-axis, this is my origin, this is the unit circle, and my poles should always be inside the unit circle. What is the reason for that? Correct. Because of stability. Alright? So my zeros can be inside or outside. Okay? I don't care about that. But my poles should always be inside the unit circle. Okay? Now let's do a few examples. Okay, so let's go with low pass. So we want also, when you're looking at the Z domain pole zero diagram, this represents zero frequency, right hand side part, goes up to pi by 2 on the imaginary axis, then goes up to pi. And this cycles through. Okay? All okay? So, this 0, pi by 2 and pi represents my frequency. Okay? So, if I have a low pass, I should have a pole close to my zero frequency, right? Because I want to pass zero, low frequencies. Okay? Yeah. Any questions?
If the pole represents passband, what happens if you put them close to the unit circle?
So we don't want the pole to be very close to the unit circle because of stability issues. Okay. You want the pole to be a bit close. It's like the pole could have coefficients like 0.9 or 0.95. Okay. Instead of just putting it at 0. Okay. And then we want to stop the high band frequencies, right? So we'll put a 0 here. All right?
And there you created a low pass filter.
Correct. Passes low frequencies, stops high frequencies. And then, based on the position, the selectivity of your low pass filter changes.
So the negative is for high and the positive is for low?
Yeah, so your frequency ranges from 0, pi by 2, pi, 3 pi by 2, 2 pi, again, it circles around.
Okay, so you leave it at the angle, a little angle?
Yes,
that
yes,
little frequency.
yes. So the whole frequency axis is on this circle and it's circling around, concentric circles. Okay?
And what's the effect of having it closer to the origin?
So it depends on the gain. So if you have closer to the origin, the gain that you have for your passband, that reduces.
Okay. And the gain is similar to the magnitude from the...
Correct.
Okay, so that's why you say you want like 0.95, so
Correct.
So you don't lose the magnitude.
We don't lose the magnitude. maintain the stability, don't lose the magnitude, and get the characteristic we want.
Oh.
Okay? Now, high pass. You guys tell me what to do now. Okay, first question, where is the pole?
What is next to 0 and the pole is next to pi?
It's inverted, right? It's the same thing.
Pole is next to
Pi.
pi. So pi is here, you have your pole here,
And the 0 is next to the 0.
0 is next to the 0. Just be sure that I can place the 0 inside the unit circle, on the unit circle, or outside the unit circle. Okay?
Can be anywhere.
Sorry?
It can be anywhere.
Yeah.
Because why don't you put the pole, like just a little bit before the 0, so you have like a very, very big angle?
Here?
No, like for example, why don't you put it at 3/2 pi? Yeah.
Here?
Why don't you put the pole there?
Yeah, so I can put a pole there.
That's even bigger pass, right? Like
Yes.
it's even more selective.
It's
Really big frequency.
it's not that selective. This is, so if you have a pole here, you'll have a pole here as well, conjugates. Correct? On imaginary axis you'll have conjugates. So you'll pass pi by 2 as well, if you want to pass 3 pi by 2 also.
That's why you put it exactly on the axis, so you don't have a conjugate.
Correct.
Can you repeat that one more time?
So if you on your real axis, there are no conjugates, okay? But as your pole or 0 moves up away from your real axis, you'll have conjugates, right? So it's not like you'll only place a pole here. You'll have a pole at the other end also.
And if
Okay.
you have like a pole in between those two, then you're going to have another one on the other side, right?
Sorry?
If you have a pole?
Yeah, so if you have a pole here, you have another pole here.
Okay. And
They
that's
always
true.
occur in conjugates.
The only way to avoid conjugates is to have them in the real axis.
Correct.
Oh.
Because here it's complex valued, right? If it's complex valued, it is in conjugates because you're dealing with real signals. Yeah.
What difference does place of the 0 make? So if it was like outside of the circle and still on the 0 axis, what if, yeah?
That just changes your magnitude selectivity. So poles always have to be within the unit circle. That's because of stability. But I can change the 0 around and get my magnitude that I want, the amount of attenuation I want, etc. Okay? Any questions? No? Okay. Now that's low pass, high pass. I'm going to do only a couple more examples because we don't have that much time. So, for all pass, there is a nice trick to it, that the distance of my pole or the radius, so this is the radius, right? So radius of pole is inversely proportional to the radius of my 0. Okay? Right?
So it's for everything or just for all pass?
That's just for all pass. Right? So, if my radius of 0 is high, radius of my pole is low, they essentially cancel each other's effect. Okay? So if I have a pole here and a 0 here, they'll cancel each other's effect because they're inversely proportional to each other, and I'll get an all pass. Because they cancel each other's effect, nothing is attenuated and nothing is filtered out. Okay? Now, for notch filter, so let's say we just want to notch out the 0 frequency. Okay? So, my 0 and my pole have to be very close to each other. correct? So this pole has the effect of passing all other frequencies, and everywhere else the effect will cancel, but at 0 frequency my 0 is at a greater distance than the pole, so it will have more effect and my 0 frequency will be filtered out. Makes sense.
I got lost with that compared to the Allpass. So in the Allpass you put the 0 outside.
No, it's not. I mean, you can put it inside also. You just need to follow this rule. This condition has to be met.
And that is the radius
Radius or distance from the origin.
has to be proportional to 1 over the radius. Oh, I see.
Okay.
So in this case,
We'll do the examples. Don't worry. Yeah.
it's just that the low pass,
Which case?
they're the same distance from the origin. Okay, it has to be 1 over the same distance. I think I get it.
Okay. Good. All right. So that's a basic way of telling the filter characteristics from your pole 0 diagram. Okay. Let's do a quick example. Okay, so the example that we are going to do is an all-pass filter example. So you'll understand it very well, and I think it is in your 2009 final exam as well. Okay, so what is given to us is that y of n is equals to 0.8 times y of n minus 1 plus x of n minus 1.25 times x of n minus 1. Okay, so have you guys covered FIR and IIR in class? No? Okay. Just a very brief intro. Don't get confused with it. There are two types of filters, FIR and IIR. So FIR is finite impulse response. Okay. So in this case, you will have y of n as a times x of n plus b times x of n minus 1, so on. Okay. There will be no feedback from your output. Now let me tell you what I mean by feedback. Here you can see a y of n minus 1 term, right?
What is that term to the left of the y of n? Is that a?
Where?
That's 0.8.
That's 0.8. That's the question that we have. Okay. So here we have a y of n minus 1. That means that I have a feedback from my output. Correct? So whenever I have feedback from my output, my impulse response is infinite impulse response. And finite and infinite actually means that so in FIR case, my impulse response will only be present for a few samples. For example, if you have sort of an averaging filter. So this is FIR, right? For averaging filter, it's nothing but 1 over 3 x of n plus 1 over 3 x of n minus 1 plus 1 over 3 x of n minus 2. Correct? There are 3 of these. For a 5 length average filter, I'll have 5 of these. But it's finite. It's not infinite. Okay. For IR impulse response, as it's evident, my impulse response will be infinite. So it can be a decaying exponential, for example, going on. Okay. So this is the basic difference. Whenever you have this feedback, your impulse response will be IR, or your filter will be IR. Your filter is IR, your impulse response is infinite. Okay? So this is just a side note. Okay? You don't have to worry about it that much. Okay, so the next part of this question is that to draw the block diagram. Okay? So let's start. what is my input? What is my input?
X of n.
Correct. What is my output? Correct. This much we got right. Okay. So next thing, I'll just put a summation or adder in between. So I have an x of n added directly. Sorry. So one arrow goes straight into my adder. The next one is delayed by 1 and then multiplied by 1.25 minus 1.25. So how do I add the delay by 1?
G minus 1.
Correct. So correct. So my ideal delay. Correct. And how do I add my gain?
That's right.
Correct. Which has a magnitude of minus 1.25. And then I just add this up. Okay. Now the final output of this adder is my y of n, right? And I have a feedback from y of n now. So how do I get y of n minus 1? Again, the delay, the ideal delay. Correct? Again, I'll multiply with the gain that I have, that is 0.8. And then add it to the adder. That's the end of your block diagram. Okay? So just practice converting your equations to block diagrams. Okay? Right. So the next question that is there, this you had in your exam also. So what are the initial conditions?
Y of
For
minus 1
this.
is 0.
X of minus 1.
Correct. So my initial conditions are x of minus 1 and y of minus 1. How do I get there? Easy way. First I find y of 0. So y of 0 is 0.8 times y of minus 1 plus x of 0 minus 1.25 times x of minus 1. Y of 0 and x of 0 are not my initial conditions. This is where my actual input and output starts. Okay, 0 at 0 index. So my initial conditions are y of minus 1 and x of minus 1. And what value should we give to our initial conditions? 0, because we want to satisfy LTI properties. Okay? So y of minus 1 and x of minus 1 should be 0, set to 0.
Why is that?
To satisfy LTI property. Otherwise, if they're not 0, you'll have a response from your non-zero initial conditions. Okay?
Is the x of minus 1 0 because of causal or something like that?
No. So LTI property is for the system, right? So my y of minus 1 and x of minus 1 becomes 0, and hence my x of n becomes causal. X of n being causal is not my reason for this. Okay? Alright. So the next is take its z transform. Okay. So what is my first step?
Y of z.
Correct. So my y of z is equals to 0.8 times z inverse y of z plus x of z minus 1.25 times z inverse x of z. Now I group the terms and find the transfer function. So my transfer function h of z is y of z over x of z, which is equals to 1 minus 1.25 z inverse over 1 minus 0.8 z inverse. Correct? Now, two questions here. What is my ROC and what are my zeros and poles? First ROC. Let's answer ROC. What is my ROC?
Greater than 0.8.
Yeah, you want the thing on the bottom.
Yes. So we'll equate this to 0. Right? And z equals to 0.8 is where my convergence does not hold.
So you want it needs to be bigger than that, right?
Because C is not equal to 0.8.
No. So we'll put mod of z greater than 0.8. Why do I have a absolute value of z? Because it represents a circle. Okay, it does not represent 1/2 of the region. So we don't write it as z greater than 0.8, we write it as absolute value of z greater than 0.8.
Do you want C to be bigger than 0.8 or to be smaller?
Bigger.
Big.
Yeah.
And that's gonna keep it in the unit circle?
Yes. So the unit circle is included in my ROC right now. If I keep it less than 0.8, my unit circle is not included in the ROC. Right? And what do we want? We want the unit circle to be in the ROC. Okay? Right? So now my unit circle is in the ROC. Correct? Now, if my unit circle, okay, next question. What are the zeros and poles?
0 is 1.25,
Correct?
also is 0.8.
Correct. So 0 at 1.25, pole at 0.8. Alright? Now, I have my unit circle in the ROC.
Shouldn't the 0 be because you oh I see, yeah, because it was C. Okay, no, it was -1.
Yeah. So 0 is at 0.5, 1.25, and pole is at 0.8. Now I have the unit circle within the ROC, so I can find the frequency response. Correct? How?
You
Substitute z is equals to e raised to power j omega. Correct? So my frequency response is now 1 minus 1.25 e raised to minus j omega over 1 minus 0.8 e raised to power minus j omega.
If you have gotten z greater than 1, that is not the ROC.
And then we can't make the substitution, then we'll have to take the Fourier transform.
We need to compute the whole thing, like the whole summation, right?
What summation?
Like to find that Fourier transform, we need to do like the whole integral or summation for negative.
Integral. Integral. Okay? Okay. So now, let's get the pole zero diagram. The final part of the question. So this is my unit circle. This is real z, imaginary z-axis, my origin. Okay. So my 0 is at 1.25, right? So it's here. My pole is at 0.8. Now, a thing to note here that my pole radius, that is 0.8, is equals to 1 over 1.25. Correct? And this results in Allpass.
Could you explain how you got that expression one more time? The 0.8 equals 1 over 1.25.
That's just an observation.
So it's proportional in 1 to 1, right?
Yeah, it's 1 to 1. It's not scaled. Okay? So if you calculate 1 over 1.25, you'll get 0.8.
So it's not so you said like it's inversely proportional to the other thing, right?
Correct.
So
I
it's
should have
like
said equal to.
equal to?
Yeah.
Yeah.
So let me correct that. I should have said equal to.
Proportional or proportional? Or exactly, have to be exactly?
Yeah.
One times.
Okay. So if it's
If I put proportional, then a scaling factor can come into the picture, which we don't want. Okay? All right.
What happens if you have more than 1 0? One, because of that, you assume 1 pole and 1 0. What happens if it's 2 poles?
We'll have to see the diagram to see that.
So if we have more than like one pole, then they can say that one each of them cancel each out and
Yeah. So if I have complex conjugates in this case, in this same case, and I have it like this, correct? Even in this case, it will be Allpass. If my pole radius is equals to 1 over 0 radius. Okay? So I can have the case of complex conjugates. All right? Okay. Any questions on this? Okay.
In the expression we have, like, we didn't simplify it. Is it like we should not simplify it? We just didn't
What
simplify
simplification?
it. Like 1 over z. So you just read z over the inverse, right?
Yeah.
So you didn't write 1 over z and then simplify it and cancel the z out.
That is only when you need to find the inverse transform.
So we can just like leave it there.
Yeah, this is just transfer function. For transfer function, we don't take the over z step.
Well, so far, we still haven't had to use. The Fourier transform, right? You can do that with a Fourier transform. That's okay.
What?
Like what you've done so far, you haven't used the Fourier transform yet, right?
Correct. Because my ROC includes the unit circle. If it does not, then I'll have to do that.
In that case,
So could you explain the graph, the unit circle graphs one more time? I don't get how you get from the numbers to the graph.
Okay, so I have my pole at 0.8, so this is 0.8. And I have my 0 at 1.25, so this is 1.25. Okay?
Okay.
And that's just directly, I just plotted directly.
Yeah.
Yeah?
And then the other one?
The other one, I'll have a complex conjugate. So I'll have 0.8 times e raised to power j pi by 4, for example. Okay? Yeah, I'm not sure if this is correct, just an example.
Yeah.
So it'll be 0.8 away in both cases, and this will be at pi by 4, and this will be at minus pi by 4. And my zeros will be at 1.25 distance. So the distance from the origin is my magnitude, and the angle represents this angle that I have.
So the first graph is just magnitude, whereas the second one is magnitude and angle?
Yes, because for this we'll have complex poles and zeros. In the first one, I don't have complex poles and zeros. My poles and zeros are real, right?
Yeah.
There's no imaginary part. But here I have an imaginary part. That's where the angle comes in. Okay?
But you still don't care about the angle, you only think about the radius, right?
Yes. You care about the angle if it's not an all-pass, if it's low-pass or high-pass.
But maybe it could happen that you have one zero, and then you have like two poles, like the zero doesn't have conjugates, but then the poles do have.
That happens. That
Or we
totally
still look
happens.
with the same equation?
Not with the same equation. So you'll have 1, 0, and you'll have 2 terms in your denominator. Okay? Yeah.
in our case, would z have to be between like 0.8 and 1 or something for it to work out? When it comes to region of convergence, 0.8 is greater, z is greater than 0.8.
Correct.
So, like it can be anything above 0.8.
Anything above 0.8.
What would happen if it's like 0.6 or something?
If it's 0.6, my region of convergence is outside.
We'll evaluate the expression at the bottom.
So
and then
if my region of convergence is, let's say, is less than 0.8, it does not include the unit circle, right? And I wanted to include the unit circle. That's why I take it greater than 0.8.
is there any way we can check that by evaluating an expression or something?
Sure, you can check that. You can substitute z equals to 0.6 in these cases and find h of z. Okay. You will either get a negative value or it might not converge. Yeah.
When you say it's not in the unit circle, if it's below that regions of convergence, what do you mean by that?
So when I have mod z greater than 0.8, this means that I have a circle of 0.8 radius and everything outside is my region of convergence. So the unit circle has a radius of 1. So my unit circle is part of the region of convergence. And that's what you want.
So if magnitude of z was less than 0.8, wouldn't the inner circle just be smaller, but like still
Yeah.
converge?
No, it won't cover my... See, this unit circle is not an area. It's just the boundary,
Yeah.
right? So if it's less than 0.8, my unit circle is outside my ROC.
Oh, okay, I see.
So it would only work for the donut shape, but not for the inside.
What donut shape?
Over there. On
This
the,
one?
on your left. Yeah, on the left. It wouldn't work for the inside, but
It won't work because your z values are only valid here,
Right.
and your unit circle is not included.
okay.
So
I
you're
guess-
using Z transform, I mean, Fourier transform in this one, right?
Yes.
I see what you're saying.
You can't make that transition from Z transform to Fourier transform then. Frequency response.
How is this an all-pass filter again? I didn't understand it.
Okay, so the radius of my pole is inverse of the radius of my zero, and they cancel each other's effect.
Okay, so that means any frequency can go through.
Any frequency can go through.
Okay.
So when my pole has an effect that it will pass frequencies, my zero has an effect that will not pass frequencies. When they cancel each other's effect, everything gets passed. Okay. All right. Now, okay, let me turn on the laptop. Here is a demo, and you can play with this demo, and I'll share it on Canvas. It's just you just download and run it through MATLAB. So once you download it, go to the folder where you've downloaded it, and then just call the demo name, and your GUI opens up. So here you have your pole 0 plot, top left, then your impulse response, your magnitude response, pole location, 0 location, phase response. So let's try a pole location of, what, let's say 1. Oh, sorry. It didn't add anything. Why are you not adding anything? Okay, forget this. Okay, finally. Now, I have a pole at 0.5 and a 0 at 0. Okay. So, my pole has a tendency of passing frequencies of 0 hertz. That is DC. Okay, so this is DC.
But it only passes frequencies 0, like no frequency at all.
DC signals. Right? DC signals have no frequency. Okay. And my 0 is at 0 distance from the origin, so it has no effect on the pole, at least. It stops the other frequencies.
So if the 0 is in the origin, then that's stop time, there's no stop time.
There is, but it does not affect the pole. That's what I'm saying. Okay. And just to show you the frequency thing, so this is your 0 frequency. It increases, and just notice how your magnitude response, the red line moves on the magnitude response. And this just traces the frequency. So this is pi. 1 over here, it represents pi. Okay? So in actuality, in your pole 0 diagram, it's not pi, it represents pi. Okay? And then it just keeps tracing. So here it's repeating from minus pi to pi. But it just overlays on top of each other. Okay?
So
Now, yeah.
under the axis, the x-axis again, is negative. Like everything's going to be negative, right?
What is,
The complex side, it's
I didn't get it.
and it's
Okay. Now let's just change this to minus 0.5, and now my pole is at a higher frequency, so it's passing higher frequencies and not passing lower frequencies.
What if it was 0.1?
What?
Minus negative 0.1.
Okay, let's put that. Okay, so let me delete the previous one. It's not very good selective high pass filter, right? They'll cancel each other's effect because they're so close to each other.
So once it crosses 0, then it becomes kind of high pass, but it depends like the selection depends on how far it is.
Yes, correct. Because here the 0 and pole are so close, they'll cancel each other's effect. Right? Once the pole is further away from the 0, its effect won't be cancelled.
Isn't that the case for notch though? Aren't they supposed to be real close to each other?
No, so here they are close to each other, but they're at the origin.
Oh, I see. They have to be at the edge of the
Yes.
circle for them to be
Yes. So let's do a notch filter.
I'm sorry, I'm getting
Confused.
Yeah, I'm getting confused as to how, because you had mentioned that, their magnitude will tell you how far they are from the origin gives you the magnitude response, right?
It shows their power, the power of their effect.
So, like for example, if you have the pole.
So let's say, let's answer that question. If I have a pole at origin, that's it. Oh, now you won't add. Why isn't it adding anything? Let me put 0.1. Okay, I just have one pole, right? And it is a very low pass signal.
It's very low pass.
I mean, it's not very selective. It's almost like an all pass, right? Now let me just put 0.9. And whatever happened to my pole 0 diagram?
But I thought.
Okay.
But Amrita, I
Yeah.
thought that the selectivity was only on how the selectivity depended only on the angle of the face. Right?
No. Here it also depends on the power. So the further away it is from the origin, the better the filter is. Correct?
It is better because it doesn't destroy the magnitude of the signal.
Correct.
But in terms of just letting it pass or not, that's only dependent on the angle of the.
Which frequencies to pass or not, that depends on the angle. So here the angle is 0, so it's passing 0 frequency and very highly selective because it's very far away from the origin. Correct? If I keep it closer to the origin, it will not be very selective.
But I thought the selectivity was, I thought the selectivity depended on the phase because that's which frequencies are it's gonna let pass or not.
So think about this. If your filter has what is the filter doing? So if your low pass filter is only supposed to pass DC, right? And if I set its magnitude to be 0, right? It will give 0 to all frequencies.
Yeah.
Correct? That's what it means. If my pass band magnitude is very low, then there's no difference between my pass band and stop band. When it's very close to the unit circle, that means I am giving a very high gain to my pass band and attenuating my stop band a lot more. Okay? The power of my filter is, the quality of my filter is increasing.
Oh, okay, so because the 0 is there, it's pretty much killing, everything it stops actually, it's like killing it because it's multiplied by 0, it disappears.
Okay. Alright, so my pole is at 0.9, let's add up 0 at 1. And there is my notch filter. Alright.
So by doing that, everything that means that like everything that passes through pretty much it's 0.9, so it passes as itself. But
Correct.
everything does not pass.
So my zero frequency does not pass. My zero frequency gets notched out. That's what notch filter is. It is throwing out a particular frequency.
How do I change that frequency not to be zero? I change the angle, right?
You change the angle. Alright?
What is the 0 is at display?
Let's see that. So let me delete this. It's again a low pass.
So it depends like which side they are in, or
Correct. My pole will have a higher effect than the zero because my pole is further away. Right? That's why it's low pass. For notch, my zero is further away. So it will notch out that frequency.
By
Alright?
notching out, do you mean killing it or extracting it?
Killing it. Okay? And I'll, yeah. You have a question?
What's the effect of the magnitude? Like,
What magnitude?
the further away it is from the zero on the pole zero plotter.
So let me show this to you again. So if it's 0.1, we see how the filter response is, right? It's not very good, right? It's supposed to pass low frequencies and not pass any other frequency. Right now it's almost passing all the frequencies, right? Because it's very close to the origin.
But when we see the magnitude response, that means, does that mean that what does the magnitude response tell us?
That tells us that my signal is coming in, it's getting multiplied by this magnitude and going out.
Oh, okay, multiplied
Okay.
by, okay, depending, okay. So like if you get a magnitude of 0, it's multiplied by the value at the top, right? Like in that
Sorry?
bell. Like, so that means if you put something with DC frequency, like 0 frequency, it's gonna get multiplied by whatever, by evaluating that curve
Correct.
at the right.
Correct. But these values are very close to 1, both of them. So it's not a very good low pass filter. Right? Now let me put 0.9. Look at the magnitude gain that I have for zero frequency. It's 100. It's getting multiplied with 100. And all the other frequencies are getting multiplied with 0. So my filter is of better quality. It's now an actual low pass filter. Right?
Yeah.
So the further away it is, the better effect it has.
But if you're multiplying it by 100, you're changing a lot. Then it's becoming really big. The amplitude of the
That's the point of passband, right?
so you want to make it like more clear and more visible.
Correct.
Why does it do that? When you make it larger, the magnitude, or wait, when you make it further away from the origin, why does it like be more selective? Like it just does.
So if you calculate the magnitude response, you have h of z expression here. If you calculate the magnitude response from here, you'll see it's because of the coefficients that you're getting. The further away it is, you get certain set of coefficients. That's 1.8 and 0.81 here, right? Those play an effect of, for each frequency, what sort of an output you're getting.
That's a bandpass, right?
This is a low pass signal.
Wait, does it for low pass have to be the pole in the positive side and then, well, it's close to 0 and then the 0 goes by?
Correct. So I can have more effect if my zero is at, so if you see my zero location, let me put it at -0.1, right? I have an even better filter. Correct?
That would be like, so how would be bandpass then? Because bandpass is like it's like the opposite of
Bandpass or high pass?
the bandpass one.
bandpass. So you'll have 0 here. Okay, let me show it to you. Let's go minus 0.5, 0.5. I should move the pole somewhere else.
This one, we see the previous
That's a
one.
bandpass. Oops, I should reduce the value. See, it gave me an error because my poles are outside the unit circle. Now it's passing a particular band. Okay?
So bandpass means that it's passing any particular band?
Yes, like 10 kilohertz to 40 kilohertz.
Oh, you make it specific.
Correct.
Sorry, how did the finite impulse response thing we talked about relate to our example?
So in our example, it did not, because our example was an IR. It was an infinite impulse response because we had feedback. If you say look at an average filter, that will have a finite impulse response. So there are two types of filters. That is just a side note that I gave. Okay? Because there's a question on that. That's why I gave that. Okay? Any other questions? Practice with this, you'll get the hang of it. Right? Give it some time. Alright, another thing that I just wanted to talk about quickly is modulation. So, don't have much time. When we come to modulation, so why is modulation done? Think of it as if you're sending audio signals, okay? All of them have the same frequency, right? And there are 10 of us sending the signals. But all of us want to communicate. But the signal being at the same frequency, we cannot, it will get mixed up, right? So modulation will shift all of those signals to separate frequencies. Okay? Higher frequencies like 1 gigahertz or 2 gigahertz or something. Okay? So baseband is my signal frequency.
There's something that has been confusing is that sometimes we get that frequency in hertz, but sometimes we get it, you know, as omega.
Correct. So omega is equals to 2 pi by t, or omega is equals to 2 pi by f, 2 pi f.
But if they give us like a cosine of ft, then we kind of
Why
we
not?
put like omega over 2 pi.
Correct. You can go either way. Okay? Alright. So baseband is a signal frequency, that is your input or your message, if you want to say. You shift this to another frequency using a carrier. Okay? And this is generally a high frequency cosine or sine. Alright? Okay? That makes sense? So what you're doing is you have your message modulated with your cosine or sine. So you'll have cos 2 pi fct or sine 2 pi fct, right? Where my frequency is fc, that is carrier frequency. Alright? The output that I have is my modulated signal, which then I transmit. Okay? That's the basic idea of modulation. Now, let me just do it from your lecture slides. Okay, another thing was bandwidth. So whenever we talk about bandwidth, bandwidth is my non-zero frequency. Okay, so on the left my bandwidth is not from minus fmax to fmax. It's only from 0 to fmax. Okay, non-negative. Okay, and for anything that's bandpass, it's this area, f2 minus f1. Okay, it's not this area. If you count this area, you will get twice the bandwidth. But your negative frequencies actually don't exist. Okay, so whenever you're asked a question about bandwidth, it's only the positive frequencies. Okay, now here we have modulation. So for modulation, we are just multiplying the two. There's no convolution. Be careful of that. My carrier is not a system. The two things are getting multiplied. Okay? So when it's multiplication in time domain, it results in convolution in the frequency domain. Correct? And the frequency transform of cosine is given in your textbooks. You have your Fourier transform tables. Correct? It's a known result that you can directly use.
That one we have it. But when we are convoluting in the when we convolute in the other, can we still use does it happen the same way it happened in the time domain?
Correct. Convolution steps remain the same. Right. So let's say that your x1 omega, your input signal is a rectangular. When you convolute this with impulses at these frequencies, you'll get two rectangles centered at those frequencies. That's what you have. The standard convolution that you do in time domain. The same thing done in frequency domain. That's the only difference. Okay? Right. So now your modulated signal. So y1 of omega is my modulated signal. It will be centered at omega c and minus omega c, and it will have a bandwidth of 2 times omega 1. All clear? Okay. Not 4 times omega 1. We don't count the negative frequencies. Okay, only the positive frequency. Okay. And anything lower than omega c is called my lower sideband. Anything more than omega c is my upper sideband. That's a term in communication area. Okay. Right. So let me just do a demo on modulation. I'll put up this code for you. So in this I have an audio of a gong. Okay, everyone knows what a gong is. And my carrier frequency is 4 times my baseband frequency. Alright. And my carrier is just calculated as a cosine of 2 pi fct. Okay. And for modulation, I'll just multiply the two directly. Time domain multiplication. Okay. Now let me run it for you. Yeah. So my modulated signal has 2 sidebands. It's again positive frequency and negative frequency. Okay. And it's around 0.3, and it's 3 kilohertz or something. Okay. 0.3 raised to the power 10 by 4, 10 raised to the power 4 is 3 kilohertz. Alright. Okay. That's, I think, all we have to cover for today. Thank you. And don't leave. Evaluations. Okay, so only use a 0.2 pencil. If you don't have one, share it into. And pencils are not on the desk. I'll be outside.
By the way, in case you didn't know, Anna, the work from here department is not in this.
Exactly. Okay, it's not in this list?
It's moved just for 2 weeks.
Okay.
I will. The office on the store. And do this fast.
I don't even know how to do it. When you the number is 80538, right? 80538.
Sparse that. Sparse that.
80538. 80538? Yeah.
What's your name?
Ya hice el mapa, ahora me falta agregar.
El mapa es una línea de código.
Ahora no me falta agregar, o sea, poner el código cuando el text sea variable, cuando el name sea var, entonces agrego esa variable a one more person.
You're going to go and submit it?
You can see.
Yeah, you can tell the head department that he's so you know, put me a header on that homework, or I'll tell you.
For question 1, where we have like Lowpass. We get it.
Yeah.
So we have that rectangular pole, so it's shifted by 1, so it's from 0 to 1, right? That is equivalent to how it is, right?
It is shifted by half.
Yeah. So it should be the same as this. 1 cosine ut and 1 minus a. Yeah. So we can do what you said. We can take this and then convolute it. The convolution of u of t is this, but it's easy because multiplying by this, it just disappears, right? Thing disappears. Once we get the, how do we find the magnitude response? So once you have the Fourier transform, how do you go from that to magnitude response?
So if you have any complex parts,
Uh-huh.
so first you group the real and the complex parts separately,
Okay.
and then do the standard complex number magnitude.
Oh, I find it, and that's it.
That's it.
And then the angle is the phase response.
Correct.
So the magnitude, it's multiplication. So if I pass a signal that has magnitude 5 and the other thing has magnitude response 2, I'm gonna get 10 out, right? And if that was 5 with an angle of 10, and then say the other thing had phase response 2, do I get 20 or 12 outside? The phase response is addition or multiplication?
Your phase is separate from your magnitude,
Yeah.
right? So if your 2 does not have a phase component, the 10 will remain the same. It gets added.
Okay, so
Phase gets added.
okay, but if I have so if you have a signal, if you have a signal, with magnitude 2 and it has an angle of 5, and this system, it has magnitude response is 5, phase response is 3. So this multiplies, I get out 10, right?
And the angle gets added.
Oh, so I get 8. Oh, okay, so, okay. The other thing regarding the filters, so we have that 4 represent fast band and 0 represent stop band. So if I have, so this big pole here, a pole here, means that only very little, only small frequencies are gonna pass, right?
So my pole is going to pass my low frequencies and its effects decreases.
I don't remember the exact syntax.
It goes to higher frequencies.
That's here.
That's what's
Or yeah, zero is more
my
stupid,
low pass
like,
filter can be
have it
enhanced
blink
by putting a 0
that
here.
you're going
Okay, that's
over.
my question.
Well, it's what negative.
Why does the 0? Oh, because stop band, so it's gonna stop the big ones.
Correct.
Okay, so this one it's only letting pass small ones, and this one is stopping all the big ones. That's why it becomes weird. Okay,
So it's an added effect.
okay, so it does the same on both. But if I put it here, then I change the magnitude. Like I'm scaling by half everything that I get, right?
Correct.
0.5.
Correct.
But in terms of which ones are passing, the same are passing. They're just coming out different.
Yes.
Okay, so the distance only changes this part, like how they're coming out.
Correct.
But in terms of identity, the same ones are still coming out. That is only affected by this.
Correct.
Okay, and if you invert it, if I do X here and 0 here, not high pass. Okay. And bandpass, you need to play around with it, right? For bandpass.
Yes.
So you get a specific
Bandpass, you can have something like you have a pole here. So if you have a pole here, you establish this big pole.
Okay.
So, and you need to pass a band of frequencies. So there's another pole.
You need to play what?
You need to pass a band of frequencies. So you have your first frequency and your second frequency.
Oh, so it only gets it in this angle, right?
And then you have zeros everywhere. A lot of zeros everywhere.
Yeah, so every iteration
Stop everything.
you're gonna
So it's messy,
see
like the bandpass is
a
hard.
T or C whatever is
So these
So-
ones are only allowing to pass, you know, say, like if
No.
this is, I don't know,
No.
this is 45,
So
Like what?
only frequencies of 45.
yes, so to increase the effect of my pose, to increase the selectivity,
From like
right? So that it only passes this region.
Uh-huh.
I have to put zeros everywhere.
Okay, and these poles don't have any effect?
They do. It's at the same
Have
frequency, right?
a
It's
dummy
at negative
variable
or
I
positive frequencies.
and have
Ah,
it
negative.
That's 5 by 2,
one
that's
integer
negative.
from 0 to 100.
Oh.
5 by 4,
100
negative.
is MATLAB starts at index 1.
I'm just sorry, just the very last, and
Have
then that notch
T
would
be a
be
separate
like,
value within your loop that you've already specified up here. And then T up in your loop. And then have T of I, V, blah, blah, blah.
When the zero is bigger than base.
So the 0 is further away from the origin than the pole.
Within
So
your
0
loop,
has
take
more
out
effect
C. Or
than
take
a
out T.
at this frequency.
at that is
And at
frequency.
everywhere else, it cancels.
Yeah, whatever, if that's in Texas.
That should have a response like this. This is at 0, and everywhere else,
No, for loop.
it's just
Like
normal.
Passes, passes by Allpass.
all fine.
Also, only
For
that
I,
only
it's
the
fine.
frequency of zero. So so if
want to go
you
from
put
1
this
to
like
100.
here, only pi over 2 dies, right?
Correct.
But you just need to put it in such a way that the 0 has more
Correct.
effect.
T of I is
If we have the x here and the 0 right here, that doesn't help at all, right?
T
That's again a low pass.
It's a low, just
equals
a low
T
pass.
plus.
However, if we put it like right here, we also have
Whatever.
another one here, right?
The
And
distance
then it's
between
gonna
them
show
divided by
another
100 is.
notch here on the negative
Correct,
side.
that's the negative.
So, like if you put the x here and the 0 here, it's a low pass, but it's not effective. It's not too good because the 0 is not helping you at all, right?
Yes.
You either have to put it here
Yes.
so that it. Thank you.
Yeah.
Homework or try to.
Tiene todo el día para terminar ese plan.
So, put the convoluted property.
Hoy, mañana.
No, porque no quiero usar
Omega is
porque quiero usarlo para mi para el lab de
Sí se puede. Dijeron que sí.
dijo que sí, que creo que prefería que nos dijera
Then
Okay, it's not like x of 2 pi f
que porque tiene que entregar
no.
y spend
So
those
it's still a pi out front. It's still like pi out front here.
You also need to have an array, like, okay, make an array T1, which is a copy of C. Make
Let me
T1
Google it
equals
for you
C.
because I had
The
a
next
hard
line
time figuring
line,
this
right,
out.
T1 equals C. Oh, yeah. Yeah, and then go down there, change that to T1. T1 equals C. Oh, this is just.
So here it's in F terms, right? A is F here.
Okay.
So it changes. It's half.
Half.
And then
Okay.
It's like dividing by 2 pi.
Maybe. This one.
This one.
Wait, you pointed that one, right?
Okay.
Okay. Yeah. Half delta f. Wait,
So that's the general F. That's your actual frequency.
minus 2 pi f. Or,
No, so your, it's FC, right?
right.
So F minus
Minus.
FC.
Oh, right. Yeah. Plus delta is plus. Now for h of omega.
Okay, you can't do X of F and X of anywhere.
Yeah, so, but it's going to be somewhat different too. But the time shift property for omega is e to the. So what's the deal with you can't just substitute 2 pi f? Or that's,
It's with the
I
actual
mean,
integration, right?
yeah, right.
It's with the actual integration.
Okay, so, but this is the time shift property for omega.
Okay, yeah.
Wolfman told me it's positive, not negative,
Let's check that.
but
Analyze an argument, analyze an issue. Yeah, but, well, no, but you have some verbal reasoning, which is, can you English?
Is it
multiple choice, or yes, it's multiple guess tests for a lot of it. It doesn't, yeah. And then
Seems to
they have
be
some
the same.
science and math stuff.
Is it computer based?
Yeah,
Um,
right after.
So the actual
So I can just.
so if I were to write h, it is negative. What's walking off a rock?
And it was like stretched because of the wire that was supposed to be. So I was there for
And everything else said it was negative.
Actually, no, it's like 7.5.
But when I typed
No, actually, like 7. Okay, usually 7.5. I mean, you get breaks, still.
Fourier transform of rect
So much better.
t minus 1/2 gave me positive for the.
I did that. Let's see if it has property here.
I don't know. It's like, what does hypnosis help you do? What's the equivalent for that? Yeah, like maybe help the patient just release. And then
Calculate.
the patient tell the truth.
Medical issues which make
What is it completely?
Yeah.
I just went to Wolfram
Yeah,
Alpha
it's like,
and
it's
Fourier
on
transform of rect t minus 1/2.
it's a good alternative to anesthetic.
But it did seem more.
And I was a little bit confused about that.
It is, like, I'd be surprised it was in there.
Sorry, Fourier transform.
Yeah.
I'm not taking it this year.
Like last escalator? Which I was like, Hillary Clinton?
Like, what about an escalator?
It was instead of great class elevator or
What
class
That's not.
escalator. And they switched it.
It is what we gave to
Women
earlier.
trying to break the class elevator in the future.
Yeah, that's
It's
positive.
like the opposite way, so like men trying to get into places where women and like,
Which,
think
I mean,
that
everyone
that's
else says it's supposed to be negative
where
exponent.
it's like more feminine, maybe.
It's possible if they think of this
Or
as
just where a lot of women are.
so
Class.
C minus
That's
A.
escalator.
You can think of A as being positive
Right.
or A as being negative. So
So-
that changes things.
Stick with negative.
Stick with the property that you have.
Okay. Yeah. So it seems like I can just do a direct substitution from that property of 2πf. Is that what that other page said?
Evolution alpha.
No, on that blue page.
Oh, let's use.
The one I think it was below this. No. Where it gave like e to the minus j 2πfa.
It must be Wolfram alpha.
What?
Is that 100 values or is it adding 100 values? If I made it for
Some other page. But it seemed to be like you did directly substitute omega equals 2πf into the property.
But
Yeah,
it's negative 5 to 1.
Right.
it does seem like that.
So here it's going to be 0.
So if I substitute that h of f equals e to the minus
Yellow quick one, and then to make highlighter yellow.
pi f.
Asian
So look at your target here.
I think it was some other
Your
page
A
on this.
is 1. Your A is 1.
Right.
The time period is 1. Right? So looking at sync
I mean, like, you just don't straight up.
of just the rectangle, not the shifted version.
Okay.
and you know what the shifted version does to it,
Okay. Right.
right? So you just add that. This square root 2 pi factor comes because you're going from f to omega.
Right. So
So in f domain, it will just be e raised to power minus a minus g
minus pi fj.
I had open properties of I don't know. It's a good idea to refer the same site.
Yeah, that might have been the page. Yeah, this page, I think.
Okay.
Yeah, that one right there. It seems they directly substituted.
Correct.
Yeah. But that would still not. This would still be gone, though.
Yes.
Right. Yeah. E to the minus. 2 pi f minus j pi f.
Your 2 and your a is half.
Right.
It gets cancelled.
H
I mean, that's your original H of it.
yeah.
You can have some other name for it, G of x or something
Yeah, I'll
else.
put GFF. So then GFF then is GFF. Well, I can just look that up, but then I'll just convolute the two.
Correct.
So, have we like covered everything?